I went ahead and titled this next page and sketched it out just to save some time. So in this situation, we actually have a regular pulley and a lever working together. So we've got the lever, and then the pulley is attached to one side of the lever, and so it's going to be lifting. We're actually applying our effort force using a pulley over here. Okay, so if we wanted to find the ideal mechanical advantage of this compound machine, so find the IMA of a compound machine with a pulley and a lever. I put a lever. Close enough. Okay, so we know one thing that we haven't gone over yet is that the total IMA of a compound machine is the IMA of all the simple machines put together. So IMA of a compound machine is the, if we're multiplying things, that's the product of all of the IMAs of the simple machines. So it's the product of all of the IMAs of the simple machines. There we go. So basically that means IMA total is equal to IMA of machine 1 times IMA of machine 2 times however many IMAs you might have. So I'll just put an N there for whatever number that might be. So in this situation, we have the IMA of the pulley times the IMA of the lever. So this is our formula. And I'm going to go ahead and substitute. So I've got I'll put total here. IMA total is equal to the IMA of my pulley. So if we look at this, how many support strands do we have? So how many of these strands are actually supporting against the load, which is basically this lever arm? Well, since we're pulling up, fighting against gravity here, we do count this arrow. So that's 1 and 2. So our IMA of our pulley is going to be 2 times the IMA of our lever. And you may know that the IMA of your lever is dE over dr. So I guess we're kind of continuing to write out a formula here a little bit. So IMA, just put a little t here for total, is equal to 2 times, let's see, our effort distance here is, oh, I wrote dr twice, didn't I? That should be dE, because that is the distance to where we're applying the effort, and that is 12 feet, and then the dr is 4 feet. So we're going to say that that is 12 feet divided by 4 feet. So IMAT is equal to 2 times 12 divided by 4 is 3. And of course, feet cancels out. And so then finally, total IMA is equal to 6. Okay, and let's see if that, yep, that matches perfectly what we get right here. Okay, here's another pulleys in combination. Let's see if we can figure out the IMA of this combination of pulleys. In this situation, we've got, this is a compound machine with pulleys in combination. So this is where multiple pulleys are actually being used together. So each of these is a separate simple machine, and because they're attached to each other, that's what makes them this compound machine. This is very similar to what you would be doing if you were using a block and tackle. If you're familiar with a block and tackle, that's something like that's where you might see a row of pulleys all together, and then you might have some strings going around between all of them. You see that a lot in like cranes and stuff. So if you're familiar with a block and tackle, this is kind of like a deconstructed block and tackle, or a spaced out block and tackle. So let's figure out what is the IMA of each of the individual pulleys. Well, if we're looking at this first pulley, it's supporting 20 pounds. There's 10 in each. This is a fixed pulley. We know that that's an IMA of 2. And we have the same thing going on here. We have a fixed pulley support strands. It's supporting 40 pounds, 20 pounds between, so that's another 2. And then this is the exact same. So let's sketch that really quick. I've got 1, 2, and 3 pulleys. This is my 80 pounds. And then on my ceiling, I've got 1 rope that goes like this, and then I've got another rope that goes like this, and then I've got a final rope that goes like this. Okay, so we have the IMA total is equal to IMA of 1 times IMA of 2 times IMA of 3. So IMA, T for short, instead of writing out the word total. The IMA of each of these is 2 times 2 times 2. So 2 times 2 is 4, times 2 is 8. Your total IMA is equal to 8. So, which makes sense because you've got an 80-pound weight, and up here where you're applying the force, you're actually only going to have to apply 10 pounds of force. That's 1/8 of this overall weight. Though it's difficult to see it from here, but if you get an actual setup with this, you can see you have to pull way farther with this rope to get this to go. Like every time like each of these ropes, you're going to have to pull twice as far, and so you're actually going to have to pull this 8 times as far. If I wanted to pull this up 1 foot, because of that IMA, I'd have to end up pulling this 8 feet to be able to balance that. So remember, the trade-off, if you're using less force, you've got to apply that force over a longer distance, because the work that you're doing is still the same. Force times distance equals work. The work is still the same We're just using a smaller force and a much longer distance. Okay, let's get one more pulley example here. We're going to actually calculate AMA of a pulley. I'm on page 5. Okay, so this is pulley AMA. AMA is going to be figured out just like any other system. We're going to still use FR over FE. Let's go ahead and sketch this pulley real quick. So here's big one, little one, little one, big one. And our weight, 800 pounds this time. Okay. These two are going to be connected. These two are going to be connected. I'm going to start out with my, I'll do a different color for my rope to make it a little bit easier to see, hopefully. Rope goes around here, and then around there, and then around the bottom big one, and then around the top big one, and we're pulling down. Okay, our effort force is 230 pounds. Pounds, sorry. The 800 pounds, this is our resistance force. Okay, so let's see if we can figure out the actual mechanical advantage. You might notice 1, 2, 3, 4. This is just like the sketch that we did right here. Orientation of the string I think is slightly different, but the IMA here would be 4. And if that were the case, 800 divided by 4 would be 200. But why might this be 230 for when we're measuring the force? Well, that's going to be due to friction. This pulley isn't 100% efficient. So we know that AMA is equal to FR divided by FE, and that is going to be 800 pounds divided by 230 pounds. And so then AMA is equal to about 3.48. No units because pounds cancels. And there we are for the AMA. Okay, now how about the efficiency of this pulley? So remember, IMA equals number of strands. So the IMA is equal to 4. The number of supporting strands, that is. Remember, we're pulling down with gravity, so we don't count this strand. If it was oriented where we were pulling upward, then we would count it because we're fighting gravity. Here, we're not fighting gravity, so we're not actually supporting anything with these. It's these 4 that are doing the support of the weight. This last one is just changing direction. Okay, so then what is our efficiency? We know that E is equal to AMA divided by IMA times 100%. So E is equal to 3.48 divided by 4 times 100%. E is equal to 3.48 divided by 4, and that is 0.87 times 100%. So E is equal to 87%. Boop. Okay. All right. One other thing that we want to address, I'm going to go ahead. Whew, this has been a lot of pages. Maybe because I'm just writing bigger. Page 6. So this is a, well, I could probably fit this. No, I already drew the line, it's fine. Page number, Pulleys, continued. Okay. Misconception alert. Angles don't matter. Well, that's not true. They actually do matter. So if you guys can see here, we've got in our first pulley, I'll do here. I've been doing all of these right in a row, so I'm starting to get tired. Here's an 80-pound force. And if we're pulling just straight up, that's actually going to be 40 pounds in each strand. But if you're actually pulling at an angle, you will see, if you were to actually test this out, let's call this 46 pounds, 46 pounds, and then in the middle, pulley. This is still just 80 pounds, but we're having to pull a little bit extra because we're also pulling outward against each other. So there's also, what's happening here is you've got some force that is acting straight up and down. This amount would be your 40. This amount would be your 40. And then there's also going to be about 6 pounds going opposite each other. So they're fighting each other a little bit as well. So angles actually do matter. That's going to change how much tension is in these strings. For the sake of this class, we're not going to get into that right away because not all of you will have had geometry and gone through right triangle trig like this, but you really could figure this out using Pythagorean theorem, but it is still a little more than what we want to really cover in this particular class. Okay, so let's go ahead and cross out angles don't matter. So this requires trig over here to be able to figure that out. This really only applies if we're dealing with strands that are parallel to the resistance force, but that's really all we're going to be covering in this unit. Okay. In this one, it says count the effort strand if it pulls up sometimes. So what I've been showing you so far, basically if we're pulling up with that strand, usually that means that we are supporting the pulley with that strand. In this situation, this is a really bizarre one. So misconception 2. So that is incorrect. In this situation, we're pulling down, but we're actually opposing. This is like we're trying to pull something down towards the floor. So if we had something that was maybe attached to the ceiling and maybe there's like a spring connected to it and we're trying to pull down and lock it into place or something, that would be an example where we would count that effort force pulling down. So let's do a quick sketch here. Here's our pulley. And then if we have a resistance force, Fr, pulling upward, and then we're attaching one side of our strand to the floor, and then we're pulling on the other side. Let's say that our FR equals 80 pounds, and that's going to be equal to 40 pounds, and then this is also going to be 40 pounds over here. Oh God, sorry, you can't see that. So we've got 40 pounds on either side here, and we would have an 80-pound force that's pulling upward. Maybe there's a spring or something else. Maybe there's another machine that's holding that, and we're trying to pull that down. That would be an example where we are counting Fe, even though we are pulling downward. So it's really about you count the Fe strand if it is opposing the direction of the resistance force. Okay? So that is the end of this lesson. So to do a quick review of what we've covered, because we actually covered quite a bit. We started way back here with the wheel and axle, and we figured out that if we are applying our effort force on the axle and the resistance force is here at the edge of the tire, that is acting like a third-class lever, because we're trying to move this whole thing by applying our force where we have a little bit of leverage. Whereas if we thought of this as a steering wheel or a knob, and we were applying our effort force out here, then we have more leverage, and that's going to be acting like a second class. We did an example of how to calculate that. We did an example of calculating AMA and efficiency. And then we talked about pulleys. We've got your fixed pulley and movable pulley. We've got figuring out the IMA. It's just the number of support strands. We don't count Fe if it is pulling in the same direction as our resistance force. So see how both of these are pulling down? We're using gravity to help us, so we're not going to count that strand. In this example up here, where we did a compound machine, the Fe is opposite your resistance force, so we are counting that strand. So it was an IMA of 2, and then to get our total IMA, we also had to find the IMA of this lever, and we used the effort distance of 12 feet. So from the fulcrum to where we were applying that effort force was 12 feet, and to the load was 4 feet. And so we were able to calculate IMA. And then we looked at a compound machine with just pulleys. And so that's when a pulley, instead of being attached at one end and then you apply a force here, it's being attached to another pulley. That's what makes it a compound machine. And so we had to multiply those together, and we ended up with an IMA, a total IMA of 8. And then we did an efficiency calculation with this example. Here, again, the strand is in the same direction as the weight, so we are not counting this one. This was an IMA of 4, and we calculated the AMA and then calculated the efficiency. And then finally, 2 misconceptions. We figured out that angles do in fact matter, because when you're pulling opposite, there's some horizontal force that's being canceled out, so the overall force in the string has to be bigger in this situation. And also, if we have basically an upside down fixed pulley, your FE, even though we're pulling with gravity, the resistance force is pulling upward against gravity, and so those are opposite directions, so we would count the effort force in that situation. And that is everything for this lesson.